Hi, I'm Dan Jurafsky, and Chris Manning and I are very happy to welcome you to our course on natural language processing. This is a particularly exciting time to be working on natural language processing. The vast amount of data on the web and social media have made it possible to build fantastic new applications. Let's look at one of them. Question answering. You may know that IBM's Watson won the Jeopardy! Challenge on February 16th, 2011. Answering questions like William Wilkinson's book inspired this author's most famous novel. And you may know that the answer is Bram Stoker, who famously wrote Dracula. Another important task is information extraction. For example, imagine that I have the following email from my colleague Chris about scheduling a meeting. We'd like software to automatically notice that there are dates like tomorrow, times like 10 to 11:30, and a room like Gates 159, extract those information, create a new calendar entry, and then populate a calendar with this kind of structured information with the event, date, start, and end for a calendar program. And modern email and calendar programs are capable of doing this from text. Another application of this kind of information extraction involves sentiment analysis. Imagine that you're interested in cameras and you're reading a lot of reviews of cameras on the web. So here's a bunch of reviews. We'd like to automatically determine from the reviews that what people care about in cameras are particular attributes. If they're buying a camera, they want to know if it has good zoom or affordability or size and weight. So we want to automatically determine those attributes. And then we'd like to automatically, for any particular attribute, determine how the reviewers felt about those attributes. For example, if a reviewer said, nice and compact to carry, that's a positive sentiment. And here's another positive example. But a phrase like flimsy is a negative sentiment. So we'd like to automatically detect for each sentence what the sentiment is, and then aggregate for each features, for zoom, for affordability. So we might decide that this camera, the reviewers really like the flash, but they weren't so happy about the ease of use. So we might measure the positive and negative sentiment about each attribute and then aggregate those. Machine translation is another important new application. And machine translation can be fully automatic. So for example, we might have a source sentence in Chinese, and here's Stanford's phrasal MT system translating that into English. But MT can also be used to help human translators. So here we might have an Arabic text, and the human translator translating it into English might need some help from the MT system, for example, a collection of possible next words that the MT system can build automatically and help the human translator. Let's look at the state of the art in language technology. Like every field, NLP is divided up into specialties and subspecialties. A number of these problems are pretty close to solved. So for example, spam detection. While it's very hard to completely detect spam in our email boxes, we don't have 99% spam, and that's because spam detection is a relatively easy classification task. A couple of important component tasks, part of speech tagging and named entity tagging, we'll talk about those later in the course, and those work at pretty high accuracies. We're going to get 97% accuracy on part of speech tagging, and we'll see how that's important for parsing. In other tasks, we're making good progress. Not as commercial, not as completely solved, but there are systems out there that are being used. So we talked about sentiment analysis, the task of deciding thumbs up or thumbs down on a sentence or a product. Component technologies like word sense disambiguation, deciding if we're talking about a rodent or a computer mouse when people talk about mouses in a search. We'll talk about parsing, which is good enough now to be used in lots of applications, and machine translation, usable on the web. A number of applications, however, are still quite hard. So for example, answering hard questions like how effective is this medicine in treating that disease by looking at the web or by summarizing information we know is quite hard. Similarly, while we've made some progress on deciding that the sentence XYZ company acquired ABC company yesterday means something similar to ABC has been taken over by XYZ, the general problem of detecting that two phrases or sentences mean the same thing, the paraphrase task, still quite hard. Even harder is the task of summarization, reading a number of, let's say, news articles that say, oh, the Dow Jones is up, or the S&P 500 has jumped, and housing prices rose, and aggregating that to give a user information like, in summary, the economy is good. And finally, one of the hardest tasks in natural language processing, carrying on a complete human-machine communication in dialogue. So here's a simple example asking about what movie is playing when and buy movie tickets. And you can get applications that do that today. But the general problem of understanding everything the user might ask for and returning a sensible response is quite difficult. Why is natural language processing so difficult? One cute example are the kinds of ambiguity problems that are called crash blossoms. So ambiguity is any case where a surface form might have multiple interpretations. A crash blossom is the name for a kind of headline that has two meanings, and the ambiguity causes a humorous interpretation. So reading this first headline, violinist linked to JAL crash blossoms, you might think that the main verb is linked and that a violinist is being linked to what? He's being linked to Japan Airlines crash blossoms. Well, what are crash blossoms? Well, this headline gave the name to this phenomenon because the actual interpretation that the headline writer intended, the main verb was blossoms. Who does the blossoming? A violinist. And this fact about being linked to JAL crash was a modifier of violinist. Similar kinds of syntactic ambiguities. So here, teacher strikes idle kids. The writer intended the main verb to be idle. The strikes caused the kids to be idle. But of course, the humorous interpretation is that the teacher is striking. Strike is the verb. And we have a teacher striking idle kids. Another important kind of ambiguity is word sense ambiguity. So in our third example, red tape holds up new bridges, the writer intended holds up to mean something like delay. We'll call that sense one of holds up. But the amusing interpretation is the second sense of holds up, which we might write down as to support. And now we get the interpretation that literal red tape, as opposed to bureaucratic red tape, is actually supporting a bridge. And we can see lots of other kinds of ambiguities in these actual headlines. Now, it turns out that it's not just amusing headlines that have ambiguity. Ambiguity is pervasive throughout natural language text. Let's look at a sensible, non-ambiguous looking headline from the New York Times. So the headline, we've shortened it here a bit, is Fed raises interest rates. Well, that seems unambiguous. We have a verb here. I'll write a little parse tree. Raises. What gets raised? A noun phrase. We'll write a little two nouns here, interest rates. And we'll have a verb phrase. So raising interest rates. And then we'll have the Fed. Make a little noun phrase. And then we'll say this is a sentence that has a noun phrase, Fed, and a verb phrase, raises. And what gets raised is interest rates. So this is called a phrase structure parse. We'll talk about that later in the course, phrase structure. So we could also write a dependency parse. So we say the head verb raises has an argument which is Fed, and it has another dependent which is rates, and rates has another, itself has a dependent interest. So we can see the main verb is raising. Well, another interpretation of the very same sentence, one that people don't see, but that parsers see right away, is that it's not raises that's the main verb of the sentence, but interest. Somebody interests something, and that something that gets interested is rates. And what is interesting these rates? Well, it's Fed raises, raises by the Fed. So we have a completely different sentence with a different interpretation that something is interesting the rates, whatever that could mean. And it seems an unlikely interpretation for people, but of course for a parser, this is a perfectly reasonable interpretation that we have to learn how to rule out. In fact, the sentence can get even more difficult. This is the actual headline was somewhat longer. So we had Fed raises interest rates 0.5%. Here we could imagine that rates is the verb. And now we have what is rating? Fed raises interest. The interest in federal raises are rating 0.5%. So we might have a dependency structure like this. So again, interest rates. The raises are what do the interesting, and the Fed is a modifier of raises. So whether with our phrase structure parse or our dependency parse, and even more so as we add more words, we're going to get more and more ambiguity that have to be solved in order to build a parse for each sentence. Now, the format of the course, you're going to have in-video quizzes, and most lectures will include a little quiz. And they're there just to check basic understanding. They're simple multiple choice questions. You can retake them if you get them wrong. Let's see one right now. A number of other things make natural language understanding difficult. One of them is the non-standard English that we frequently see in text like Twitter feeds, where we have capitalization and unusual spelling of words and hashtags and user IDs and so on. So all of our parsers and part-of-speech taggers that we're going to make use of are often trained on very clean newspaper text English, but the actual English in the wild will cause us a lot of problems. We'll have a lot of segmentation problems. For example, if we see the string YORK-NEW as part of New York, New Haven, how do we know the correct segmentation is New York and New Haven, so the New York, New Haven Railroad, and not something like York-New? This word here is not a word like in-law. We have to solve the segmentation problem correctly. We have problems with idioms and with new words that haven't been seen before. And we'll also have problems with entity names, like the movie A Bug's Life, which has English words in it, and so it's often difficult to know where the movie name starts and ends. And this comes up very often in biology, where we have genes and proteins named with English words. The task of natural language understanding, it's very difficult. What tools do we need? Well, we need knowledge about language, knowledge about the world, and a way to combine these knowledge sources. So generally, the way we do this is to use probabilistic models that are built from language data. So for example, if we see the word maison in French, we're very likely to translate that as the word house in English. On the other hand, if we see the word avocat général in French, we're very unlikely to translate that as the general avocado. And training these probabilistic models in general can be very hard, but it turns out that we can do an approximate job of probabilistic models with rough text features, and we'll introduce those rough text features as we go. So our goal in the class is teaching key theory and methods for statistical natural language processing. We'll talk about the Viterbi algorithm, naive Bayes, and Maxent classifiers. We'll introduce n-gram language modeling and statistical parsing. We'll talk about the inverted index and TF-IDF and vector models of meaning that are important in information retrieval. And we'll do this for practical, robust, real-world applications. We'll talk about information extraction, about spelling correction, about information retrieval. The skills you'll need for the task, you'll need simple linear algebra, so you should know what a vector is and what a matrix is. You should have some basic probability theory, and you'll need to know how to program in either Java or Python, because there'll be weekly programming assignments, and you'll have your choice of languages. We're very happy to welcome you to our course on natural language processing, and we look forward to seeing you in following lectures.